Thank you everybody to joining us today for this second conference, Japan, Luxembourg. My name is Sylvain St-Amand. I'm the head of the international relations at the University of Luxembourg. Very happy to be the moderator today. And we're so happy at the university to collaborate with the Embassy of Japan with this series of conferences. We had one last week on the 5G, 6G, and XG in communication, which was extremely interesting. And I think that today you will find, I will let the ambassador present our lecturer today. I have some instructions, perhaps, before we introduce our conferencier today. This will be recorded, and it will be posted on the embassy's website, the embassy's YouTube channel, and at the very end of the conference we'll give you the URL so that if you want to share it with colleagues and friends or listen to it in another time. As it is recorded, we would ask you please to mute your microphone and turn the camera off. Usually during a class we like to see everybody, but for this recording we would rather have just the Professor Sugiyama's video on. For the questions, we would ask you to, as the conference is unfolding, put your questions on the chat, and at the end of the presentation I will try to put them together for Professor Sugiyama and go through them. This is the second conference that I was saying. We have another one coming in at the end of November. Please check the embassy's website and our website to get the date exactly of when it will be held. The conference today will be in two parts, or let's say 4 parts. Professor Sugiyama will talk about the large topic on artificial intelligence. Then we will have some questions, and it will be followed by a shorter presentation on much more technical terms and on the research that Professor Sugiyama and his team are conducting, and then we'll have other questions. So it will be like in those 4 parts. So I talked enough. Kanemitsu, perhaps we could listen to the ambassador's remarks before turning to Professor Sugiyama.
Yeah, of course. Thank you, Sylvain. So, unfortunately, Mr. Ambassador, Mr. Jiro Okuyama cannot attend this meeting. So, but he gave her a video message. So I will play it from now.
Ladies and gentlemen, please forgive me for not being able to attend today's meeting and instead send you this message by video. As the Ambassador of Japan to the Grand Duchy of Luxembourg, I am pleased to welcome Dr. Sugiyama Masashi, Director, RIKEN Center for Advanced Intelligence Project, as a speaker for a webinar co-hosted by the University of Luxembourg and the Embassy of Japan in Luxembourg. Today's lecture is titled AI Research in Japan, Challenges at RIKEN Center for Advanced Intelligence Project. Artificial intelligence is now in its 3rd boom. Big data, machine learning, deep learning. Nowadays we see these terms in the newspapers every day. The fact that they have become so common that everyone has heard of them proves the growing interest in this field. In fact, some of the technologies have already started to reach us. Maybe one of the closest examples for us is an assistant program installed on our smartphones and tablets, such as Siri, Google Assistant, and Alexa. In Japan, Pepper, the robot developed by SoftBank, has become very popular due to its friendly appearance. Advertising optimization, automatic translation, automated driving, traffic congestion prediction, medical and nursing care, logistics, the applications of artificial intelligence are wide and hopeful. The RIKEN Center for Advanced Intelligence Project, AIP, is working on the AI technology development from various viewpoints. Its director, Dr. Sugiyama, is one of the top Japanese scientists in this field who received a number of awards, such as the Faculty Award from IBM in 2007, the Young Scientists Prize by the Minister of Education of Japan in 2014, and the Japan Society for Promotion of Science Award and the Japan Academy Medal in 2017. Today, I am delighted to introduce you to the cutting edge of research in this field in Japan, thanks to such a talented Japanese scientist. I'm looking forward to watching the recorded video that will be uploaded to the embassy's social media after the event. Thank you very much, and I hope you enjoy.
Professor Sugiyama, the floor is yours.
Okay, so let me start. Can you see the slide?
Yes, everything's fine.
Okay, so then let me start. Okay, first of all, so thank you very much for the kind invitation today. So I'm quite excited to be here. So my talk is about AI research in Japan, challenges at RIKEN AIP. So I'm Masashi Sugiyama from RIKEN and also the University of Tokyo. So before starting, let me briefly talk about RIKEN. So what is RIKEN? So it's actually a Japanese research institute. So name in Japanese is Rikagaku Kenkyūjō. It's 6 letters like this. So this is pronounced as Rikagaku Kenkyūshō. And Rikagaku basically means this is physics, and this is chemistry, and this is like subject or something. So first 3 letters mean physics and chemistry. Then Kenkyūjō, Kenkyu is research, and Shō is institute. So this is research institute. So RIKEN means Physical and Chemistry Research Institute. So that's the entire meaning of RIKEN. But Japanese people prefer to make longer word into the short form, and we call it RIKEN. So Ri here and Ken here, so RIKEN. So that's the pronunciation here. And in the end, so RIKEN decided to, call us RIKEN, even in English. So that's the name. So I'm from RIKEN. So here's a brief history of RIKEN. Actually, RIKEN is quite old. So it was founded in 1917, so more than actually 100 years ago, as an actually private foundation. So one of the founders is actually a famous person called Eiichi Shibusawa. He's actually now quite famous because we have a TV program for him. So he's actually a founder of many big companies in Japan. So then actually RIKEN had a kind of conglomerate. So it's called RIKEN Concern. So in 1939, RIKEN actually had 63 companies and 121 plants. So it was really a huge conglomerate. But World War II finished in 1945, and US unfortunately broke down RIKEN. So it was broken down completely. But in 1948, so RIKEN restarted as a Scientific Research Institute Limited. It's called KAKEN in Japanese. Then after that, in 1958, RIKEN became public corporation. So maybe this form is the basis of the current RIKEN. So then after that, RIKEN grows and grows, and then finally, so we had the centennial celebration 4 years ago, and now, so 2021, so we are here. So our president is Hiroshi Matsumoto. Then RIKEN is a national research center having many different research centers. So this is a bit busy slide, but we have about 10, more than 10 research centers, and roughly, so we have like many physics research centers and some medical research centers, biology, neuroscience, and also informatics. So 2 informatics centers, and one is high performance computing, and the other is AI center that I belong to. RIKEN has nice infrastructure. Maybe this is different from the biggest difference from the universities. So RIKEN has a big infrastructure, like Spring 8 and Sakura. It's a huge accelerator in the mountain. Or RIKEN has the world's fastest supercomputer, Fugaku. So this is currently the #1 fastest computer over the world. And also it has many different factory and some technology. And also the RIKEN is supplying bioresources. Then here's a rough revenue and expenditure of RIKEN. So roughly RIKEN revenue is 100 billion Japanese yen per year. So this is approximately 770 million euro. And half of them is coming from the government funding. And another 1/4 is for maintaining the large facilities and some other things here. Then expenditure, so we have research project and research infrastructure management and also operation of big facilities and things like that. Then the number of personnel here. So about like 40 years ago, 35 years ago, RIKEN was not so big. But around here, so late 1990s, RIKEN started to have fixed term research centers. Then, so it actually grew quite fast like this. So RIKEN started to hire many fixed term research staff. So around 2005, we have almost the current number, and the number is kept the same for around 15 years now. RIKEN is also quite international, so we have a large number of international researchers. And because we are in Asia, so we have a lot of Asian researchers, so including China, India, Korea. But we also have people from Europe a lot. So actually 1/4 is from Europe. But unfortunately, when I see the list here, I can't find Luxembourg here. So it's quite unfortunate. And hopefully, like, through this presentation today, we can have like visitors from Luxembourg, or maybe we can have more collaboration together in the near future. So now we have about 800 researchers coming from 65 different countries and regions. Then RIKEN also has many overseas offices. So RIKEN offices are in Europe, Brussels, and Beijing, and Singapore. And at the same time, we have many like joint research labs. And actually, there's one in Luxembourg. So RIKEN Luxembourg Joint Research Labs. So I will talk about this in the next slide. But we have already one in Luxembourg. And more precisely, so RIKEN and Luxembourg has actually nice relations already. So this was the announcement released in 2015. Actually, I joined RIKEN 2016. So this is before I joined RIKEN. But so representatives from RIKEN and the Luxembourg National Research Fund gathered at the embassy, Luxembourg embassy in Tokyo, and they signed a memorandum of understanding. So this MOU covers all areas of science with special focus on immunology and systems biology. So we had Ambassador Kirsch and also FNR Secretary General Mark Schlitt. And also from the RIKEN side, so Center for Integrative Medical Science, IMS, and also Luxembourg Institute of Health and Luxembourg Center for Systems Biomedicine. So they are already collaborating together. Then, so 2 years ago, so 2019 August, RIKEN opened joint laboratory with the University of Luxembourg. So this is the University of Luxembourg's Luxembourg Center for System Biomedicine and the Luxembourg Institute of Health, together with the RIKEN. And again, so this is joined by like Center for Integrated Medical Science from RIKEN, and also like a Medical Science Innovation Hub program from RIKEN. Then also, I found the latest news from our webpage. So actually, December this year, so 2 months from now, so there seems to be a symposium, so 2021 RIKEN Luxembourg Scientific Symposium. So this is Luxembourg Center for Systems Biomedicine of the University of Luxembourg, and also the Luxembourg Institute of Health joining, and they seem to call for participation and call for presentation. So if you are interested in this event, so you may take a look at the webpage of RIKEN to find more information. Okay, so this means already RIKEN and Luxembourg has nice relation, and after that, so RIKEN started AIP, so our center, Advanced Intelligence Project. So let me briefly talk about our RIKEN center. So what is RIKEN AIP? So RIKEN founded Center for Advanced Intelligence Project in 2016 under Ministry of Education, Culture, Sport, Science, and Technology. Next. So our main office is located actually in the heart of Tokyo. So, Tokyo is quite crowded, and RIKEN's headquarters is a bit away from the center. So RIKEN has a huge campus, but it's a bit away from the center, maybe 1 hour away from the center by train. But our center is located really in the heart of Tokyo. It's actually 10 minutes walk from the central Tokyo station, a building like this. This building is not ours, but we are on the 15th floor somewhere here. And first 4 floors are actually shopping mall. Then, so inside this building, we have a nice open discussion space. My background is also here. So this is not a fake image, but this is our office. So we invite researchers here, and sometimes we have a seminar here. We also have in-house GPU servers. And so not only in Tokyo, but we have many distributed offices across Japan, like from Sendai to Fukuoka, like Kyoto, Osaka, etc. Then, so our center, AIP, has 5 missions. The first mission is to develop next generation AI technology. So this is basically, basic research. So we are interested in developing machine learning and optimization theory and things like that. Then the second challenge is to accelerate scientific research by AI. So in particular, we are interested in cancer research, material science, and genomics and things like that. In those areas, the use of AI is really mandatory nowadays to boost their research. So we are supporting their activities. But whether cancer, material, genomics, so these topics are quite popular in Japan. So that's why we chose these topics. Then the third challenge is to contribute to solving socially critical problems in Japan. For example, we suffer natural disasters a lot. Like just last week, we had a slightly bigger earthquake in Tokyo, or we have typhoons and we have tsunami. So we actually suffer a lot of natural disasters, and prediction and also things like that by AI is quite important. Also, elderly healthcare is a quite important and urgent topic for us. Because now Japan is like a super aged society. So we have a large number of elderly people supported by a small number of young people. So unfortunately, Japan is a kind of front runner in terms of the super aged society. So we really need the help of AI to support elderly healthcare. Then the fourth topic is a bit different. The first 3 topics are more like science and technology. So we had like science researchers. But the fourth one is the study of ethical, legal, and social issues of AI. So to work on this topic, actually, we have like social science researchers, humanity researchers, and also even lawyers in our center, and discussing ethical guidelines of AI, or we are discussing how to manage personal data, etc. And finally, human resource development. So we still need more researchers and engineers in AI, but still the number is quite small, unfortunately, in Japan. So we try to help growing researchers and engineers in this field. So these are 5 missions we are tackling. Then this is the rough statistics of our center. So our center is luckily quite diverse. So we have 140 employed researchers now, and 30% are international people, and 20% are female researchers. Maybe this ratio is weirdly low compared with Luxembourg, but as a research center in Japan, this number is reasonably good. But we hope we can improve this ratio more. Then we have about 300 visiting researchers from different universities, and also about 60 domestic students as part-time workers. And then we also have 140 international internship students from over the world. So these are actually great things. So we invited many students from different countries, and many are also from Europe. And before the Corona pandemic, so we had 140 students so far. But after the Corona pandemic, we had to stop the internship program now, and it is stopped now. So hopefully we can resume the program, and hopefully we can invite students from University of Luxembourg in the near future. Also, we are interested in the collaboration. And inside our center, we have 3 industry collaborative centers. So together with NEC, Fujitsu, and Toshiba. In addition to 3 centers, collaborative centers, we have 40 more industrial projects, from small one to middle-sized ones. And also we have 40 more international collaboration partners, like from Europe, from North America, and from Asia, Middle East, and Oceania. And again, hope we can have more collaboration with University of Luxembourg in the near future. So EU, so European Laboratory for Learning and Intelligence Systems, ELIS is a EU organization, and maybe this could be partly related to Luxembourg. So AIP's research challenges. So machine learning is the core technology of current AI, and our center is based on machine learning basically. The goal of machine learning is to let the computer learn like humans. And the application of machine learning is very successful in various areas like speech recognition, image understanding, natural language translation, or online advertisement and things like that. But the current machine learning still has many limitations. And most typical ones are data hungriness, meaning that current machine learning requires big label data for training the system. And also another critical problem is its black box nature. So this means that current machine learning model is less interpretable. So its judgment is not clear by human. So our challenges at AIP are as follows. First, we developed new machine learning theory to overcome these limitations. Then second, we try to explore new machine learning applications beyond current machine learning. Then finally, we hope to contribute to designing new machine learning society with appropriate ethical discipline and data circulation system. So these are our major challenges. And today I briefly talk about our lines of research along them. Okay, then so the contents today are as follows. So in the next 3 parts, I will talk about our machine learning research on application or society and theory. Then here I stop once. Then I take questions. Then after that, I will talk about my own team's research. That's more on basic machine learning things. Then finally, I will conclude my talk with future challenges. Okay, then so let's start machine learning application part. The first topic is cancer diagnosis, in particular prostate cancer diagnosis. Actually, prostate cancer accounts for about 10% of male cancers. So this number is actually coming from National Cancer Center for Cancer Control Center in Japan. So, but I think the number is quite similar in Europe and other countries. About slightly less than 10% are stomach cancer, colon cancer, lung cancer, but prostate cancer is actually highest, about 10%. So automatic diagnosis is really desired because we have so many patients in the hospital. And for this purpose, a standard approach is to use supervised machine learning technique, supervised classification. But unfortunately, to use supervised machine learning technique, we need annotated pathological images. This means that we need to ask medical doctors to find whether there exists a cancer in this pathological image or not. And this actually takes a lot of time, even for medical doctors, And also there are like hundreds or thousands of images to be inspected. So this simply increased the burden of medical doctors. In particular, they are extremely busy under this corona pandemic. So it's actually not really possible to collect a large number of annotated pathological images. So we decided to use unsupervised deep learning technique for feature extraction. Unsupervised means so there's no annotation, and we only collect unlabeled pathological images. That can be rather easy. Like we just measure, we just take images, and that's it. In the end, we used more than 11 billion unlabeled pathological image batches like this, and for feature extraction. Then we applied rather standard like autoencoder type feature extraction system. Then, so we found that in addition to the standard Gleason score, so I'm not a medical doctor, so I can't really tell what it is, but I heard that Gleason score is a kind of standard one to evaluate the cancer. But in addition to this Gleason score, the novel features such as interstitium change were discovered automatically from unsupervised deep learning. Interstitium change means if we are interested in evaluating whether this cell is cancer or not, then actually it is important not only to see the inside of the cell, but also the area outside the cell plays an important role to judge whether this cell is a cancer or not. So that's a finding here. Then so we decided to use those new features in our system. Then actually the prediction of 1 year recurrence was improved a lot. So this is so-called the AUC score from 0 to 1, and 0 is poorest and 1 is the best. And if a human expert pathologist does the evaluation prediction, the score was 0.744. But our system actually already goes beyond a pathologist, and score was 0.82. And more interestingly, so if we combine these two, so pathologist and our system, then the score is further boosted than 0.842. So it's the highest. So combination of human and AI really improved the performance. So that was a great finding here. And now, so the same kind of technique has been applied to like iPS cells. So stem cell research is also quite popular in Japan, and also leukemia and breast cancer. So the technique itself is quite general, and it has a large area, a large variation of applications. Okay, the second issue is called ghost cytometry. So this is also a very interesting application. So we are interested in classifying cells. For example, we are growing iPS cells, stem cells. Then some are growing nicely, but some are becoming cancer. Then we want to get rid of those cancers. But if we do this manually, it takes a lot of time because cells are very small and it takes a lot of time to classify them. So here we use the system called flow cytometry. So here's a thin pipe, and we fill it with liquid. Then the cells are going through this pipe. Basically, we do like automatic classification of cells. And here, so image is taken, and then so deep learning is running here. Then cell is classified here. And if this becomes cancer, so it is turned, and here's a trash box, so it is thrown away. If it's a good cell, then it is kept here. But because this is a liquid, so it's quite fast. So standard deep learning inference is actually too slow to run in real time. So deep learning inference is too slow. So here actually we decided to use another new technique called ghost cytometry. So why it is called ghost? Because we don't really take the image of the cell itself, but we use a specially designed illumination pattern like this. Okay, this is already like features extracted by deep learning. So this pattern already includes some information, and this illumination is given to the cell. Then we have already extracted the features directly. Then the classification can be done immediately, resulting in real-time classification. Now this system is becoming really real, and we found a startup for industrialization. And it has been applied to like tumors and iPS cells so far. Then the third topic is earthquake cycle prediction. So I don't call it earthquake prediction because it's more like fortune telling. So I don't really say earthquake can be predicted, but earthquake cycles can be somehow evaluated. So here's a map of Japan. So Tokyo is here and Osaka is here. And there's a Nankai Trough, south of Japan, is located south of Japan here. And this Nankai Trough is expected to cause a big earthquake in the near future. So expected epicenters are somewhere here, so quite a broad area. So risk assessment is really necessary. Since this is a big social topic in Japan, so a large number of researchers have already worked on this topic, and there's a powerful mathematical model so far. It is an equation of motion of ocean plate, shear stress, and land plate friction force. The model is like this, and they have nice equations like this. But here, actually, the issue is, so there are actually a lot of parameters like friction parameters, and those friction parameters have index I, and this index I actually depends on the location. But as I said here, so expected epicenter is quite broad. So I actually is quite a large number. So we have a lot of places and we have a lot of friction force parameters here and there. So then tuning a huge number of friction parameters is really a big headache. So this is the key. So model is good, but there are so many tuning parameters. So, and we don't have enough supervised data for this purpose because we have rather frequently earthquakes in Japan, but still the number is quite limited. So, and that number of earthquakes is not enough to tune these friction parameters. Then here's a new idea called simulation-based machine learning. Basically, we use a simulator to generate artificial data, pseudo data. So more specifically, we alternately perform simulation to generate artificial data by induction. Then we perform learning by training a model with artificial data. And this is repeated until convergence. So parameters are generated and then simulators are run. Then data is generated, then parameters are learned, and this is repeated. Then interestingly, the prediction of earthquake cycles is really significantly improved. Like before using this technique, naive method yielded about 100-year prediction error. So given the scale of earthquake, 100-year is still somewhat useful, but its error is quite big. So in our daily life. But now with our simulation-based machine learning, the prediction error is about 10 years or even less than 10 years. So this is quite practical. Then finally, so AI-based education support. So this is also quite important for young people. And actually, we started this project because actually we had the new entrance exam system for the university from last year. And there was a plan to introduce the essay writing for students. The student has to write essays, then professors have to evaluate those written essays. So somehow we wanted to automate this process. But because of this COVID-19, so unfortunately, this introduction of essay writing was postponed. So, but now we are using this system to like teach and learn how to write good essays, because teaching and learning, writing essays is quite difficult. So our system can automatically evaluate the quality of short essays. And inside the system, we use semi-supervised learning and self-training to overcome the small sample problem. And also in this system, explainability is quite important, because if a system said, our AI system said, oh, your writing is just score 10 out of 100, then so maybe we are not happy, or maybe the evaluation itself is biased, or maybe AI is useless. So we want to know the reason why it's on this score 10. So to meet this requirement, so our system output prediction confidence and also shows base cases, so that like even teachers and students both can know why this essay was evaluated in that way. So now the interactive system is running like this. And our system was actually trained only from 200 to 400 supervised data. So even collecting 200, 400 data was rather time consuming, but only from these small numbers. So human level evaluation performance can be achieved. So this is really practical system now. Okay, the next is machine learning society research. The first topic is AI ethical guidelines. So this was started in 2016, so 5 years ago already. So we have contributed to the discussion of privacy, fairness, security, etc. Like Japanese Society for AI started to discuss ethical guidelines in 2017, and our members play a central role in this committee. And also the Ministry of International Affairs and Communications in Japan had AI research and development guidelines. And later this was proposed to OECD in 2017. And also this MIC had AI utilization guidelines in 2019. And our members also play the central role in these committees. Then Cabinet Office of Japan, so they had social principles of human-centric AI. And later this was proposed to G20 in 2019. So our members also played a crucial role in this committee. Then finally, more internationally, IEEE, so Institute of Electrical and Electronic Engineers. So it's one of the biggest WE society. So they have ethically aligned design in 2019, and our members contribute to this design. And we are also interested in personal information management, so called personal life repository. So the question is, how should personal information be managed? Maybe big companies can collect data and they use them, or government may collect data and manage them. So there must be many different systems depending on the countries. So at AIP, so we propose an individual-based system. This basically means the data subjects control data accessibility. So that means we don't really give data to somebody else, but we manage our data by ourselves by encrypting our data and putting it on the public cloud like Google Drive or Dropbox. Because it is encrypted, basically no information leakage, and we manage it by ourselves. And also it's quite low cost for deployment because we just use public cloud, so it's quite cheap. And it's scalable to like tens of millions of users. And as a proof of concept, we had like thousands of high schoolers sharing their learning records with school management system. So this was done last year, and this year we are extending the scope of this project to more government-related public data management. Okay, the fourth one is machine learning theory part. So let's go this part rather briefly. So we are interested in understanding current machine learning technology, particularly deep learning. So deep learning basically stacks many layers, like from input to output. There are several hidden layers. And because of this layered structure, actually optimization is quite hard. So in each edge, so we have tuning parameters here. So there are a large number of parameters and they need to be optimized in the learning process. But this optimization is quite complicated and it's quite difficult, challenging to find the global minimum. But in practice, it works quite well in many real-world applications. So this part is still rather mysterious mathematically. So we are tackling this problem with mathematicians and even some physicists who are good at mathematics. Then so we proved some superiority results mathematically. Like even though optimization landscape is complicated like this, actually global optimization is possible with high probability. So by adding actually some small noise to the gradient direction. And also like before deep learning, so people used techniques like support vector machine or some other machine learning techniques. And those methods were actually said to suffer curse of dimensionality. So this means that data is high dimensional, then solving the problem is getting exponentially harder. But for deep learning, we could successfully prove that for high-dimensional data, actually the curse of dimensionality does not happen for deep learning because of this multi-layer structure. So this was mathematically proved. Then finally, so we answered the question of how rich the deep model is. So there are actually many different types of deep learning architecture. And for a particular architecture called inverse neural network, we showed its universality, means that it can approximate arbitrary function with arbitrary accuracy. So these are mathematical results. And then another very interesting and challenging topic is called causal inference. So let me briefly talk about correlation and causality. So here's a nice graph. The horizontal axis is the amount of chocolate consumption. Then the vertical axis is the number of Nobel Prize winners for each country. Then very interestingly, so the correlation, it has very high correlation. So actually correlation coefficient is 0.79. So this basically means that we can predict the number of Nobel Prize winners of that country by looking at the chocolate consumption, amount of chocolate consumption, because they are correlated. So that's correlation. But causality is different, meaning that, so if we want to increase the number of Nobel Prize winners, so eating more chocolate does not help, right? So this is clear. This means that so the amount of chocolate consumption and the number of Nobel Prize winners are correlated, but there's no causal relation between these two. To see the causality, so randomized control trial is a standard approach, like in medical trial or some social experiment. There, so in randomized control trial, so we split the subject into two groups randomly. Then treat one group and see what happens. Like give real medicine to one group, then just leave the other group or give some fake medicine. But this treating only one group can be ethically problematic. In particular, if you talk about like medicine or vaccines, because of non-treatment, maybe the patients may suffer from that. So this is a big problem. So we want to avoid doing randomized control trial in this kind of context. Then the causal inference technique appears. But in causal inference, actually the presence of hidden cause is a big challenge. Like in the previous case of chocolate and Nobel Prize winners, actually the real cause is GDP. So money was actually important. If a country is rich, then the rich country can have much chocolate and also many Nobel Prize winners. But if the country is poor, so the amount of chocolate consumption is low and also the number of Nobel Prize winners is low. So GDP was actually a hidden cause. But we don't observe this directly. So for this kind of problem, so we developed the first method to estimate the entire structure of the causal graph in the presence of hidden cause. And interestingly, technically, the speech separation technique is employed to separate hidden cause from observed causes. So that's an interesting technique. But now we can, for a small case, so small scale case, we can discover the entire structure of the hidden cause. Okay, so until here, so we tried to cover broadly the activity of RIKEN Center for Advanced Intelligence project. And I would like to stop at this point, and if there are some questions, I would like to take them. So Sylvain, can you continue?
Yes. Thank you so much, Professor Sugiyama, for this presentation. There's a lot of content, and I'm not sure I understood everything, but we have had a few questions, and one is, I was going to ask the same question, is about your AI-based education support. Because we are in a university, people are very interested in learning more about that. So the first question is that, is it based on the written structure of the text or from specific topics that are predetermined in the entrance examination? So on what do you base the good or bad essay that you are evaluating?
Yeah, so thank you very much for the great question. So, okay, this is based on the entrance exam. So there's a like problem, a question. Then students write a short answer to those questions. So there's a kind of ideal answer made by, I don't know, professors or some other people. So then basically, so people can somehow relatively evaluate the quality of students' answer. And we want to predict those scores automatically from written text.
So is it based on the words that are used, the relationship between the words? Can the system detect the logics behind it?
Yeah. So it's actually a big system. So not only superficially evaluating the sentences, but it really try to understand the meaning of it and structure of the sentence. So it's not simply like a deep learning translation kind of stuff, but it really try to like deep understand the meaning of the sentence.
Can it write essay?
Say again?
Could once that you know what is a good essay, could it write it on my behalf, for example, so that I can be admitted in your lab?
Yeah, that's a very good question. So evaluation is still kind of the first stage, right? So generation of essay is really another big challenge. So nowadays, like people use like unsupervised deep learning to generate like characters or human's face, but logical structures like sentence is quite challenging now. So we hope that we can also contribute to this field in the near future.
Let me know when it works. There's a question. I'm going to read the question because it's to me it's a little bit technical. So Salah Gamizi asked, you mentioned your research about robustness and fairness. Do you work on real use cases, or is it mostly theoretical vulnerabilities?
Okay, thank you very much. So first, okay, as basic research, so we do really fundamental things. So without really specifying real applications. So that's a general like research attitude. But at the same time, we have like several real world collaborations, like human, like elderly healthcare or medical research. In those fields, so we clearly have very specific, challenges like robustness and also reliability and things like that. So in the latter half, basically, it's really application dependent. So we can't really call them like generic research, but for each application, we have like a team of people who are really working on those concerns.
I guess that answers the question, but I'm not sure exactly. Salah is happy with the answer, so I guess it's all right. One of the things that I read a few years ago, it was about the bank who were using AI to determine if a loan should be given or not. And the assumption is that it's perfectly objective. But since it was based on past decisions, who were tainted by sometime gender issues or race issues, they found that the loan applications was treated not in an objective way. So I'm guessing that you are now beyond that, but how would you answer this?
Yeah, thank you very much for the great question. So I would say that we are working on that topic from two different aspects. So one is like a technological aspect. Like, okay, data has bias. Then, so we want to somehow debias the data, or we want to debias our prediction system. And this is a like mathematical topic, and this is actually becoming quite possible now. So then, okay, the next question is, what is like unbiased? What is fair? This is another question. Maybe this depends on the country or culture or application domains. So then, like from that viewpoint, maybe society has to decide what you mean by fair in this application or in that situation. So once we have a kind of common understanding of the fairness, then we try to express it in terms of mathematics. Then the system can really meet that kind of fairness constraint or things like debias constraint. So I think the technology is already almost there, so we can use it. But still, the society side is a bit behind that. So we need to really work with each application or practitioners to discuss what the real fairness is in their applications.
And I guess it's a moving target in various societies.
Yeah.
So the poles are moving, right?
True,
And
true.
your job is just to follow this. Okay, so I have a few questions, but I invite all the participants to post some.
Yeah,
Here's
that's great.
one.
Thank you.
Here's one is in Luxembourg, we have different institutes, the LIH, Health, LCSB, SNT. How are research groups split at RIKEN? Is RIKEN AIP, your institution? Is it an equivalent of our own Center for Cybersecurity and Reliability in IT? So what's the link between your various research groups or institutes? Like your center, for example, how independent is it from the higher management?
Okay, so RIKEN has several different centers here, and our center is a bit special because usually RIKEN headquarters has a big research funding like this from the government and use that for running research projects. That's standard for other centers, but our center AIP is actually a special project run by Ministry of Education for 10 years. So we have actually special subsidy for this project. Of course, it comes through RIKEN, but this is like especially reserved for like advanced intelligence project. So that's why our center is a bit independent of other centers from RIKEN in terms of funding. But in terms of research, of course, there's no border. So whenever we can find good partners to collaborate, so we always try to do something together.
I guess as long as you control your budget, you're fine. Back to one of your application is about earthquake, and you were quite of saying that the earthquake errors at 6 years and a half was pretty good. What does it mean? Does it mean that you can predict an earthquake in 6 years, or I wasn't sure what it meant, the prediction error?
So it's the cycle. So it is. So I'm also not really an expert of earthquake research, but so it is said that there's a cycle of earthquakes. So it comes like every 150 years or something like that, depending on type of earthquakes. So this is either like 150 years or 140 years. So we can actually fit the model for the last, I don't know, 300 years or 500 years if we have historical records. But still, like we want to make prediction, and already we have recorded data in the last, several hundred years, and we have big model, big simulator. But once we tune the parameters quite carefully, still the simulator's output is quite different from the truth. So already, like there was a big earthquake in like 1475 or something like that. And after 150 years, there's another big earthquake here and something like that. So we try to fit the model, but fitting is of course possible. But if we tune the parameters, physical parameters from the real measured values, then the prediction error is so huge. So maybe the model is not accurate enough, or maybe tuning of parameters is not accurate enough. But at least if we tune the parameters very carefully with this simulation-based machine learning, then the error shrink quite much. And now 6.5 years out of, let's say the range is something like 100 years.
Okay, so
prediction of earthquake is rather fortune telling kind of thing. But still, cycle is the history says there's a cycle, and we try to estimate the cycle of earthquakes.
Thank you. Back to the deep learning of machines, and the objectivity or fairness that you were talking about.
Mm-hmm.
At one point, you talk of the black box, where the machine would acquire some knowledge that we do not understand, and that's the scary part. This is where sci-fi movies are made, where the AI is making decisions that the human beings did not want it. Could you expand a little bit on this black box?
Yeah, so thank you very much for the great question. I also like this point very much, and I'm thinking two aspects for this. So one is like interpretability for researchers or AI engineers, and the other is interpretability for like ordinary users of AI systems. And for the former, for researchers, actually we want to know so why the prediction is going well. Well, if it fails, so we want to know what was wrong with the system. So by looking at that, okay, we can improve the system. So to do that, we should really know the behavior of the trained model mathematically. So that's one thing we are doing now. So then the second aspect, so from the user's viewpoint, so this is again very challenging. So suppose autonomous driving car hits a child, and maybe the child died because of this. Then so maybe parents want to know what was wrong with the AI driving car and who was responsible for that. So to do that, we need to really see the system. And maybe it is possible to say that, okay, in image recognition, so this pixel was a child, but it was not recognized nicely or something like that. But maybe this doesn't really answer the question of their parents, the parents, right? So they want to know, so who really killed our child and who take the responsibility of that. So again, that part is a social part, right? We need a legal system or some understanding between users of autonomous driving cars or entire society. So this part needs to, I think, more discussion. Even insurance company may join this, and we need to really have a kind of regulation, hopefully, over the world. Otherwise, we can't really, make the system that can be responsible for this kind of thing.
That's where your example of the chocolate and the Nobel Prizes was so interesting to me. Between the rough correlations, and instead looking at the causality, this is what the car should be doing. Learn from the fact that he's coming in a school zone, might be right. There's something about the learning about the causality, I guess. I thought the example was pretty good. Could you expand a little bit on that with the car example?
Yeah, that's a very good point. So there must be a lot of hidden causes in that case. And also, even we are not quite sure what was the correlation in that context. So current deep learning can utilize correlation to make prediction, like either this pixel is a person or not, or something like that. Okay, from that viewpoint, we can say that, okay, this system made a mistake because not only this pixel, but other surrounding pixels are, something different from what we have learned in the system, or something like that. I mean, this kind of cause can be found if we are lucky enough. But still, maybe this doesn't really answer the question again, right? Maybe the explanation we want to have is not really
Oops.
right in natural language, for example. So from a technical viewpoint, still there's a big gap between explainability among the research community and explainability in real society. Maybe to fill the gap, still maybe I can't really say so what is really missing at this point. But I must say that there's a big gap still between these two communities.
And then the very interesting question is that how plausible is it that an AI machine develops a conscience of its own conscience of its own thinking? That it becomes with a character, a personality, or
yeah. Thank you very much for the great question. So when I have a discussion with neuroscience researchers, we often have this kind of topics. I'm from computer science. Then I regard AI as just a computer program. So I make a program and I run it. Then I can stop it. Then there's no consciousness from that viewpoint, and it's not autonomous. So I'm just running a program to help me. But for neuroscience researchers, they may feel like AI is already living as a creature. So Mr. AI is already living. So then they may want to think, so some notion of consciousness may exist behind AI. Still, at least in my community of machine learning, so this kind of research has not really been done well, because current machine learning is really just solving a prediction problem mathematically, and it's not more than that. There's no creativity there, no consciousness there. But nowadays, the community is trying to find a challenging topic called continuous learning. So now we try to train an AI system in a lifelong manner. So giving them many different tasks sequentially, then hope that it really learns many tasks without forgetting previous experience. And through that kind of process, we may think that some kind of like autonomous activities may exist, but still like I cannot really directly connect these two. So in terms of research, like I like to discuss that kind of consciousness kind of thing, but still as a research topic, there's still a big gap between these two, and I can't really find a direct connection so far.
So you're not afraid of a computer taking over the world in the coming years?
Not at all. Not at all. It's just a program.
Maybe a last question.
But actually, this is actually really true in computer science. Nobody thinks like AI really beats human or something like that. It cannot happen.
Okay, well, I guess that is reassuring for all of us. Last thing about your Fugaku computer. You're saying that it's the fastest in the world right now.
Yeah.
How long can you hold on that first position? Because there's a lot of, I mean, the American, the Chinese, everybody is trying to develop a faster computer, right?
Yeah. So previously, RIKEN had K supercomputer. That was so I'm not from that center, so I don't know the number exactly, but it was, let's say, about 80 years ago or something like that. Then it was #1 for a few years. Then after that, okay, it becomes second and fifth and 10th and 20th or something like that. But then after 5-6 years, it was broken down because we are installing new computers. Then now Fugaku became #1, and it is kept #1 for I think more than 1 year now. So, but of course, in the near future, maybe US or China may have even bigger computers, and they will become #1. But maybe not really, being #1 itself is not that important, right? Either we can solve many, difficult and challenging real-world problems can be solved or not. So in a sense, from that viewpoint, Fugaku is quite nice because it is really more like application-oriented architecture. So it's quite user-friendly, and also deep learning can be run there. So our center is also planning to use Fugaku extremely in the very near future.
I'm sure that our researchers would be very happy to use it as well. Perhaps we can finish this part of the presentation. You wanted to have some minutes to present your own research from your group.
Yes.
So perhaps I can give you some minutes to do that.
Okay, so let me come back to my slides and let me briefly talk about my team's research on machine learning. So my team is called Imperfect Information Learning Team. So we are interested in training a system from imperfect information, imperfect data. So we have many colleagues in the center and in the team, and actually many are Chinese. But we have many great visiting scientists, junior research associate, part-time students, and also interns over the world. So then the goal of our research is to develop novel machine learning theories and algorithms that enable accurate learning from limited information. Because collecting data is really a bottleneck nowadays. So in particular, we target learning from data with insufficient information. Actually, learning from small data is mathematically not possible. So statistically, we need a large number of data to have accurate estimation, unless we have some special prior knowledge. So we try to use insufficient information, like we may use noisy data. Nowadays, we have data collected by human or sensors, then they are full of noise, but still maybe we can easily collect many of them. Or some data contains only weak supervision. Maybe I can't really explain what I mean weak here, but I will use another slide for this. We can easily collect cheap, weak data. Or data bias. We can have biased data easily, maybe from some previous tasks or some other tasks. Because of changing environments, maybe data have some bias. We need to cope with it. But more recently, so we are also interested in coping with attacks. So nowadays, AI systems can be attacked by adding some special noise or by changing distribution of data. So this kind of security issue is also becoming quite challenging nowadays. So these are our topics. And I will briefly talk about two things. So one is learning from weakly supervised data. Like let's consider a simple binary classification problem. So let's say given like pathological image, so we want to know whether cancer exists or not, yes or no, positive or negative. And to do so, we need fully supervised data usually, like positive data and negative data. Then we can learn the boundary between these two. But data collection costs might be quite high, and also sometimes we can't collect data because of some privacy reasons. And our approach is to utilize weakly supervised data that can be collected easily. So let me show some examples. So the first example is called positive unlabeled learning. So we want to separate positive data and negative data, but because of some reasons, we can't really have negative data at all. But we only have unlabeled data. Unlabeled data means we don't know whether they are positive or negative. For example, if we consider click prediction, so we can easily collect clicked links by users. So they are positive data that users like. And also we can collect unclicked links that user didn't click. But we can't conclude that those unclicked links are links that users don't like. Or maybe users are too busy to click those links, although they like them. So that means unclicked links are still unlabeled. They can be positives or negatives. Then in that kind of scenario, we only have positive data and unlabeled data. But still, we want to separate positive data and negative data. Then, so I don't really go into the technical detail here today, but we could really solve this problem. So given only positive and unlabeled data, we can really make a classifier that separates positives and negatives. So that's one like technological advance here. Or maybe I skip this. Another example is positive confidence learning. So now, okay, suppose we are interested in purchase prediction. So I'm running a company and I want to know whether my customers want to buy this product or not. Then I have already my own company's customers list. Then, so I can really evaluate them. But because of privacy reasons, I'm not allowed to access database of other companies at all. Then that means we are not actually allowed to get even unlabeled data. So we can only have positive data in our company. Then, okay, learning from only positive data is actually not possible. But we found that if positive data is equipped with confidence, like this point is 70% positive, or this point is 20% of positive, or something like that, then again, we can train the classifier actually mathematically optimally. So that's positive confidence learning. And more interestingly, even from two sets of unlabeled data, actually we can train the classifier. So this is actually a surprising result. So suppose, so there are two hospitals, and we can collect data from these two hospitals. Then, okay, we have many medical images from two hospitals, but they are all unlabeled. But still, even if they are unlabeled, as long as their like patients' rates are different, like one hospital may have 50% patients, and another hospital may have 40% patients, or something like that. If patient rates are different, then only from two sets of unlabeled data, okay, we can train a classifier that separates positives and negatives. So that's actually quite unintuitive, but mathematically it became possible. So only from unlabeled data, okay, we can perform supervised classification. So that's the biggest finding in this research, weakly supervised classification. Then another topic is learning from noisy data. Maybe this is more intuitively natural. So what we are thinking naturally is like classification with clean data like this. So class 1 here, class 2 here, class 3 here, and we want to separate. We want to learn the boundaries. So this is the standard case, and it works already. But in real world, because of maybe human error or sensor error, labels are often flipped like this. So mix them together. But still, we want to train a classifier. But unfortunately, under this kind of noisy label situation, so standard machine learning does not work. even if we have big data, it does not work mathematically. So that's a problem. So we need actually a new method to cope with label noise. But then traditionally, the people try to get rid of outliers by looking at data. So this is easy, but it's statistically very difficult and it's not reliable. Then usually in the research community, so we use so-called robust statistics by using robust loss functions or regularization techniques. So these are like standard popular approaches in current machine learning. But unfortunately, they are not robust enough. Like if we have many noisy data, maybe this kind of robust statistical techniques do not work quite well. So we want to go beyond the limitations of these existing approaches. So that's our current challenge. And we have actually one simple method here. It's called clean sample selection. So this is quite interesting. Okay, let's use deep learning. Then actually it is empirically known that deep learning can memorize clean data faster than noisy data. So in experiments, this kind of phenomenon is quite clear in many cases. So that roughly means if we train a neural network, deep learning model, then stopping ARIA is actually better. Because if the model is trained too much, then it overfits noisy data and it doesn't work well in practice. But naively stopping ARIA, it's called ARIA stopping. Naive ARIA stopping, unfortunately, does not work well in practice. Then, so we developed a new method called co-teaching. So in this co-teaching method, we actually use two neural networks, A and B. Then each neural network is trained independently and choose small loss data that are regarded as clean data. Basically, ARIA stopping is applied to both networks. Then select promising data and teach them. So A select clean data and teach them to B, and B select clean data and teach them to A. And this is repeated until convergence. Then surprisingly, we can nicely get rid of noisy data, and the model is trained only with small loss clean data. Then in the end, so in some experiments, so we randomly changed the label, 50% of labels completely, but still our training method worked well, meaning that half of data is just noise, but they are automatically removed, and the model was trained from the remaining clean 50% of data automatically. So that was a like super robust classification technique that we are developing recently. Okay, so that was the brief introduction of our research. Then finally, like future issues. So maybe some of you are quite familiar with history of AI. So there was like classical AI studies in 1960s and 1980s, maybe first boom and second boom. So symbolic logic AI or expert system. In parallel, there was a research community of neuro-inspired AI coming from like neuroscience and neuroengineering. So they also had two booms in 1960s and 1980s, like one layer perceptrons or multi-layer perceptrons. But in 1990s, so these research areas are becoming quite shrunk because they don't work so well in real world. Then statistical machine learning research has started in about 2000. So these areas focus on like statistics or Bayes approach or convex optimization, kernel methods, and things like that. So this method becomes quite popular, and many IT companies started to use it. Then the current deep learning is basically a combination of like 1980s multi-layer perceptron model and 21st century statistical machine learning. So then 2010s, so stochastic gradient, gigantic deep models are really the basis of deep learning. Then what comes in the future? So I think, so this part is quite important. So we have already forgotten this classical AI, but this logical based thinking is also quite important. It's another mode of intelligence than neuro-inspired ideas. In 1980s, the system became so huge and it was not really processed nicely. But now we have deep learning, quite advanced deep learning technologies. Maybe combining the state-of-the-art deep learning with like this kind of logical AI, expert system AI could be a next generation AI. By that, we may integrate different modes of intelligence, and maybe we can have human-like AI or something like that. And then, this is maybe almost the last slide of my talk today. So is human-like AI really an ultimate AI? So that's a question. Maybe that's related to the question I had in the middle. So I personally believe human AI needs not be autonomous. So I hope future AI may learn together with humans. So I thought this because we had actually a fashion show at the University of Tokyo together with Professor Aihara at the University of Tokyo and also professional fashion designer Emma Rie. So she's really a famous fashion designer. And then we used popular deep learning techniques like generative adversarial net or neural style transfer and generated some ideas, best ideas, and showed those ideas to her. Then she had some inspiration from those ideas, best ideas, and had new illustrations or new writings, new drawings. Then we used them to train the network system again, and then gave her back another feedback. And this process was repeated several times. Then in the end, she really had amazingly beautiful dresses like that. And we really had a fashion show in the university campus. Then from that viewpoint, so it's actually quite nice to have like AI and human learn together. So we can also learn from AI, and AI can also learn from us. So like supporting each other would be a kind of style of next generation AI. And to do so, AI needs to be more inclusive to human society. So that's the biggest challenge to us. So technology versus human creativity, culture, ethics. So these parts are really important. But still, like machine learning is really just technology, and like creativity, culture, ethics. These are like humanity topic, and unfortunately, still these two areas are quite far. But in the near future, we need to really merge them and have really like human inclusive AI, so that we really have nice AI society in the future. Okay, so this is the last slide. Thank you very much. ありがとうございました。
Thank you so much for this very positive conclusion. When I was hearing about your research, and I'm so far from your world, but here's my question: when you do research, how much is a blackboard working on equations, and how much is statistical trials? You just run something and see what's happening. And I mean, I'm simplifying, but could you explain a little bit the process of your research?
Yeah, like in my team, I think people are rather mathematical. So many students are, and many researchers are really writing equations and proving something on the whiteboard or on the note. So, but still, like machine learning is always related to data. So once we have a nice theory or a nice algorithm, so we need to really validate our, theory with data. So we collect some benchmark data and try our algorithm, whether prediction works well or our hypothesis can be really proved by data. So then they also do a lot of programming. So we really need, mathematics and programming in the same level. So both are really necessary in this community. I can't say only one, but both are important.
So there's still a lot of work done on equations and
Right. Actually, the difficulty is that like we have also many like data scientists here and there in industry. So they are very good at using machine learning techniques and programming. But suppose they made some program and they fed some data into the program and it doesn't work. Then what should they do? Actually, just debugging the program is not a problem because the program is correct. But the problem is actually the algorithm or statistical theory behind. Then actually not the program, but we need to fix the theory behind, algorithm behind. Here actually we need mathematics. So this is actually the difficult point of AI research, machine learning research. So not only program, but also mathematics is needed. But not only mathematics, but also programming is needed. So doing these two at the same time is actually a big challenge in current computer science. But I think young students are really flexible and they are extremely powerful in learning both topics nowadays.
That's a nice conclusion as well. I think that we will stop here because you must be very tired and it's getting close to your sleep time. I want to thank you so much, and thank you to the participants, and particularly to those who provided some questions to animate and feed the discussion. So thank you to everybody, but of course in particular to you, Professor Sugiyama. It was very, very interesting. So we can do some virtual applause to your presentation, and thank you so much.
Thank you very much. Thank you very much, Sylvain, for the nice chairing the session.
And on the chat, part of of our work, you'll see the link to the YouTube channel of the embassy. So if you want to share it with someone else or re-listen to some parts of Professor Sugiyama's presentation, which was extremely rich, please, you'll find that on the YouTube channel. Thank you also to the colleagues from the Japanese embassy, Kanimatsu, and she's gone. Elena, for their collaboration, and my colleagues at the University of Luxembourg. Professor, I hope that you will have a chance to come to Luxembourg. We welcome you and would love to continue this discussion. Thank you, everybody.
Thank you very much.
Okay.
Bye-bye.
Bye-bye. Sayonara.
Thank you very much.
Sayonara.
ありがとうございました。